one of the most defining things, not just for our future, but for the future of the planet and all of life on it, is climate change. And it's not something that is somewhere abstractly in the future. It's something that's already occurring now, and we can observe its effects in some places around the globe. And usually these effects are more severe in places that are inhabited by people that have fewer resources to deal with it and that have less responsibility for these effects that have been generated already by human activity on the planet. We know that climate change will become even more problematic for us in the future, and the consequences will be even more severe. And so for inequality, the consequences will be very significant and will be felt all over the world, disproportionately, as usual, by some people that are already more vulnerable than others. But this very big and abstract topic is often difficult to understand on a more concrete level. What does it mean exactly to know something about climate change? How can we make predictions about what happens to the lands once the climate will start changing more severely? How can we get information? What is this information like? And what do million-year-old rocks have to do with it? And how can we use them to know something for us about our future? This is what we want to talk about today with Dr. Victoria Fernandes. Victoria is a geoscientist researcher at the GFZ Potsdam in Germany. She's a Brazilian researcher specializing on geomorphology. And she has gone to the edge of the world to collect many kilos of old rocks, analyze them, and tell us something about what they know already about our future. Let's join Victoria for this conversation on Future Frame TV. I'm Elise Krozer, your host for the Inequality channel. And let's have a look at what the stones say. Victoria, welcome to the program.
Thank you. Thank you so much for having me. It's a pleasure.
The pleasure is mine, is ours, because we want to talk to you today about an aspect of inequality that we have touched upon to some degree, which is the historical part of inequality. But today we want to talk about the very historical or ancient history or even prehistory part of it, because we want to talk about how inequality is built up over 1 million years and how we can know about that when we look at stones. I have a very unsophisticated view of your highly technical and very important and interesting work. Could you tell us, Victoria, what you do as a geomorphologist and how we can relate that to our current inequality aspect or inequality problem stemming from climate change?
So geomorphology is just the study of how the Earth's surface is changing and has changed in the past. So the idea is that we can use our understanding of present day processes occurring on the Earth's surface. So most notably erosion. So erosion caused by glaciers, by rivers, by coasts, and how these operate in the present day. And we can look at rocks in the past to understand how these processes might have been different throughout or have changed throughout Earth's history. So part of what I study is actually how we can use novel techniques to quantify erosion rates. So the idea is that at present day, you can't really just walk down to the bed of a river and say, I know how fast it's eroding. We actually need to know where this river used to flow in the past, but we also need to know when this river was flowing in a different place in the past. So part of my work is actually going out into the field, so going to different locations around the world, collecting rock samples, bringing them back for analysis, and to actually be able to date them. And in this way, we can both understand an erosion rate, but also know when these different erosion rates happened. And how this links to the climate record is if we have an age or if we know what certain processes were occurring at the Earth's surface at a given time, we can tie these to our climate records that we can get from, for example, ice cores in Antarctica or Greenland. And we can see, okay, so maybe erosion rates were at this particular place were higher when we were in an ice age or when the world's climate was colder, or vice versa. And we can start making predictions and understanding, okay, so what this means for the coming future. We are leaving a glacial period and well into what we call an interglacial, so where we've got a warming climate up ahead. And we don't really know or really understand what's going to happen to our landscapes. So we all live on the Earth's surface. We depend on water to live. We depend on farmland, and we need to understand whether the rivers are going to flood, where rivers are going to flow, whether these rivers are going to carry lots of sediment and completely cover the farmland or not. And so all of this is part of landscape change, and we need to understand where it's going into the future. And the key for us to understand how much it's going to change or how it's going to change in the future is by looking at past landscapes. And so this is how I'd say my work ties into climate change and sort of the human aspect of landscapes is, we depend on land, right? Things are going to change and we need to know how and how much.
And the current changes in climate, they're fairly, by historical standards, fairly fast, right? The recent decades have seen global warming. How accurate can you estimate your changes in the past? If you say you go a million years back, can you see some developments like the one we are seeing now? Or is this completely extraordinary? Or how can we get some kind of a dimension of what's going on?
So this is something that geologists and geomorphologists and climate scientists have been studying for a long time. And really, there are some clues in the geological past that we can look at and find in rocks that tells us something about past climate and how we understand, how fast climate change might have happened in the past as sort of analogs. In the same way that we need to look at the Earth to be able to understand Mars, we need to look at our past to try and understand what's happening right now. And so I'd say pretty much there's one instance that I think a lot of geologists like to look at, which is, I think, probably the closest thing that we've observed in the geological past that is as similar as to what's happening today. So about 55 million years ago, we had this big event called the Paleocene-Eocene thermal maximum. And all this is this one blip in time in which the world experienced unprecedentedly fast amounts of heating, also unprecedentedly high amounts of carbon dioxide in the atmosphere. So the exact causes of this very giant, very fast release of carbon dioxide into the atmosphere is still unknown. Some scientists postulate that these are giant methane sips that happened offshore, where you might have had some sort of destabilization of rock and you have this giant release of methane. Other scientists suggest that it might have been sort of this global surge in wildfires. So there's all sorts of postulations as to why you might have had this very huge and very fast release of carbon dioxide in the atmosphere. But one thing is certain is that it was very fast and that it was accompanied by an equivalent very fast rise in temperatures. And this is observed globally in the geological record. So this is kind of a well-known marker. People travel around the world to try and put their finger on this sort of geological event. And it's super studied because exactly for this reason, how this is probably, I think, that one of the few and maybe the only analog to what is happening right now. And even still, this sort of, when we call this geologically fast, like extremely unprecedented amount of heating and carbon dioxide that went into the atmosphere, it was so geologically fast, but it's no matter how fine a resolution that we can get on this information, so how well constrained it can be, it still suggests that it's still a lot slower than what we're observing today, both in terms of global heating and as well as in terms of increase in atmospheric CO2 levels. So, and during this event, this sort of old heating event 55 million years ago, we observed all sorts of crazy things. So the world's climate went a bit cuckoo for a few thousands of years afterwards. There are certain mass extinctions. but the planet itself recovered, given enough time, sort of atmospheric and ocean feedback set in, the temperature dropped back down, carbon dioxide levels also dropped back down, life slowly recovered. I think the difficulty here is, how is this going to happen when the rates are even faster? So I think there is still some, let's say, uncertainty as to exactly what's going to happen in the future, because I think this is just geologically unprecedented. Like, we've not really observed this kind of things happen in the past, or if they have happened, they've just not been recorded. So it's just people have used the geological past as kind of found these analogs, but even still, they are not super good, I'd say.
So if we use this marker, we should be not worried about the planet, but just worried about us? Or
yes,
probably we won't be there to record the next event.
Yes, exactly.
That's very difficult to imagine, I think, for most people, not being there. I mean, even on the individual level and as a human race more generally. Could you speak a little more about, you glanced over these huge consequences, but could you say something more about the consequences that something like this event could have today, just to get some more concrete idea, maybe, even though it's speculation, of course, because we don't know, but maybe an analog to these ancient events?
Yeah. So from what we generally understand about the carbon cycle and how carbon, ocean, land masses sort of interact with that respect, is that when you have a very, very large increase in carbon dioxide into the atmosphere, we sort of get these two things happening. So first we have warming through a greenhouse effect. And the second, so the greenhouse effect is basically just turning the world into a literal greenhouse. So if you ever step into a greenhouse, it feels a lot warmer than the outside. And that's because the ceiling keeps the heat in. So the carbon dioxide in the atmosphere acts to keep the heat inside the planet rather than letting it sort of escape back into the universe, as it usually does. And the second thing is, once the atmosphere starts increasing in carbon dioxide levels, a lot of that carbon dioxide then gets absorbed into the ocean. So the ocean acts as a giant buffer for our planet. So whenever there's a lot of carbon dioxide, it starts getting sucked into the ocean. So that is in one of two ways. So that is just by kind of diffusion. So there's a sort of a sort of exchange between the gases in the atmosphere and the gases that just sort of exist within the ocean. So the ocean just absorbs a lot of that carbon dioxide. The other way that it works is that a lot of our organisms and microorganisms that live in the oceans build those shells out of calcium carbonate. So calcium carbonate is limestone, which, as some of you might know or may not know, is something that really easily dissolves. So acid rain, for example, is a fantastic thing to dissolve statues that are made of limestone. So it effectively does the same thing. So the shells and the calcium carbonate in the ocean, present from the shells of these microorganisms, starts pretty much acting as a kind of way of sucking up the carbon dioxide from the air. So the carbon dioxide leaves the air, gets into the ocean becomes more acidic, and then these shells start being corroded by the acid that is formed inside the oceans. And so the big danger for all of this is that you start having a lot of these microorganisms, as well as other normal organisms like coral reefs, start getting dissolved. So things that we see in these sort of, famous nature documentaries about coral bleaching, that is a consequence of, say, of ocean acidification. And corals, on top of the biodiversity, they're great. But really, I think the biggest danger is microorganisms that we don't really see. So they just live floating in the open ocean, and they provide a lot of our world's oxygen. If the oceans start acidifying too much, they start getting dissolved, they start dying out, and we have to start having some problems in terms of actual oxygen production, that, or the oxygen that goes into the atmosphere that we breathe. So that is where we start having these sort of big consequences. We start having a big die out of species in the oceans. On top of that, sort of ocean temperatures start warming up. A lot of life that lives in the ocean starts dying out. Again, on land, we start seeing consequences as well in terms of forest fires. We start seeing landscapes, which is sort of my area expertise, start being destabilized because we get a change in climate patterns. So we might see an increase in things like landslides. You get melting of glaciers, which changes water regimes and water supplies to places. So places start drying up. So there's all sorts of havoc starts reefing through the atmosphere ocean system. And it becomes really hard for life to exist because life needs stability. Life needs seasons and the constant, knowing that the climate is going to be a certain way at a certain time of year. And when you start changing that, it becomes very hard for species to survive on their own, which is why we have these sort of episodes of mass extinction, or have been observed in the geological record when you have these sort of extreme climates. So these are just a few of the things that kind of start happening or that have known to happen in these past events with large carbon dioxide releases and really large temperature increases.
I know you don't usually look so much at animals like us humans and plants, and mostly at stones. So I want to ask you about the redistribution effects that this could have, because of course also it's a global event. It will affect all life eventually. And until then, probably there are some distributional struggles over who gets the last oxygen and the last drop of water. But without getting too much into those details, I'd like to existential threats. I'd like to ask you about how specifically you do get to this information, because you obviously research them in a concrete place and at a concrete location. And what do you look for, and how do you find this information? How do you get it? How can we imagine your day?
So there are different kinds of information. So it depends on exactly what aspect of these sort of climatic changes or impacts of climate change that you are trying to examine. So in my specific field, what I'm trying to look at is erosion rates, right? So one of the things that we really want to know is, say, in what I work is, for example, when climate heats up and we start melting glaciers and we completely lose glaciers from the planet, what might happen to, say, the erosion and the landscapes around these areas? So if you just think about, the distribution of that around the world, the only places that we can really study that nowadays is where we actually observe glaciers. The places that we can go to study how glaciers are actually affected by climate change is where we have glaciers today. And that is something super important because so many communities nowadays are still dependent on glacial meltwater as a primary source of water for living, for irrigation, for, just general life. Glacial meltwater and glacial valleys also feed a lot of dams that are used to generate power through hydroelectric power stations. So we really want to understand, how these systems and these landscapes are going to change, because are these landscapes suddenly going to be completely covered in sediment? Is water just going to fill up? Are these rivers just going to fill up with new sediment and stop flowing? Are they suddenly going to be diverted somewhere else? Or is the flow of water going to be so big that we're going to start getting sort of these catastrophic events? So we really need to start thinking about how these climate changes might affect landscapes. And for our case, as you said, we have to go to physical places to actually study them. And so the place that I'm studying right now, and that is part of a project I'm working on, is looking in southern Patagonia in Argentina. So that is the southern tip of South America, if you don't really know. And it's a beautiful, beautiful place. It has one of the largest ice sheets that are still preserved on land. It has these beautiful, beautiful glaciers, and I'd say it's partly UNESCO World Heritage Site. So you have these massive glaciers, but it's also a very barren landscape. It's very sort of rustic farmland, a lot of sheep farming, a lot of cattle farming. It's also a place where there's a lot of investment that people are thinking of making. So there's the specific area that I'm studying, which is close to El Calafate and Los Glaciares National Park in Argentina. They're building a dam along the river that comes out of these glaciers. So understanding really how erosion is going to change over time is massively important, because this is a huge bit of infrastructure that's being built. One of the ways that we measure actually how this erosion rate has changed in the past is we'll go to the field and we actually have to measure something. And you can't just walk up to a river and pick up a little bag of sand and say, aha, this is how fast the river's been eroding. We actually need to know two different things. We need to first know where the river was flowing in the past. So relative to where the river is flowing present day, how high above the present day level was it flowing? So what elevation was it flowing? But also, when was it flowing at this sort of higher elevation? So we need to do two things. So the first is that we sort of identify these ancient riverbeds, and they usually just look like a bit of a stair step beside rivers. So what we call them river terraces, and they're actually really common around the world. They're really easy to find. So we look for these river terraces, which are just markers of past levels of where the river used to flow. And then we collect some rock samples from these ancient riverbeds, and we take them back to the lab. And in the same way that we can use, say, carbon dating to date, say, cave paintings or, date old human skeletons, we can use beryllium, which is just a different element, to date these old river surfaces. And they can give us dates that range anywhere from close to present day, so a few thousand years ago, all the way to about 1 million years ago. So that's a really big time span. Geologically, that's just a blip, but on human time scales, that's a really, really long time. But it's the way that we have to estimate sort of erosion rates. So erosion rates is a specific point in the river. So that is what we do. So with these two things combined, if we know where the river used to flow in the past and when they used to flow there, we can start getting at an erosion rate as to, how fast the river has been down cutting into the landscape. And the other thing that we can do is, once we have these ages and we know, at these episodes at which the river sort of changed its elevation, it changed its path and started really digging into the landscape, we can start comparing it to the climate record. And we can start saying, okay, so maybe there is a time when climate change was getting hotter. So, and this ties into a time when the river started really eroding faster. So maybe we can start saying like, okay, when we have hotter climates, we're expecting rivers to erode faster. And because we have erosion rates, we can actually put numbers to that. And we can say, okay, so if the climate became this much hotter, rivers eroded this much faster. And we might be able to say something about, okay, if we're going into the future, if climate change is going to get this much hotter, if we're going to warm by 5 degrees, this is how much we expect these glaciated catchments and glaciated rivers to change in their erosion rate. So specifically to where I'm working, we'll be able to say to the people building the infrastructure, we might be able to say, hey, you might need to be worried about your turbines getting clogged up by sediments, because we're sort of predicting a massive increase in erosion rate, or things, or completely different things. They might say, actually, these guys might be fine. Erosion rates maybe don't change that much. They change it when we go back to a really cold climate. So in actual fact, things might be okay. These are questions that are still unanswered. And so this is really at the forefront of science. And it's, I guess, what really drives me to want to pursue my research and these kind of geological, geomorphological questions, because landscape science for me is really at the forefront of where human life interacts with climate, right? Because it really is where climate change has a tangible impact on our infrastructure, on our land, and on our resources. So it's this kind of research that really ties climate change to a place, is going to a place, and they're trying to really answer these kinds of questions.
And also where it becomes more personal, right? Where you can get an idea or at least an intuition of what dramatic effects could ensure after such changes, massive changes like riverbeds changing their course or the rivers changing their height, etc. But on that personal level, how do you get to look at something like that? I mean, what drives you, or what maybe got you interested in this in the first place? How did you end up looking at these stones?
I think what really got me into, I'd say, geomorphology is exactly this aspect of change, is, how it's this, you can be sitting by a river, by a stream, and it's really pleasant and it seems like a really quiet landscape, something that seems like it's been there for forever. But actually, when we look at the past, we know that rivers are extremely dynamic, extremely powerful agents of change, and they really drive a lot of what happens in the surface of the planet. If you just think about glaciers and, rivers and glaciers, and how those things really, really drive landscape change, and how, they really shape the surface, and you can see a landscape and you see, wow, this looks amazing. It looks amazing because a river or a glacier flowed through there and shaped it that way. So I think, to me, on a personal level, like, that is really what drives me and interests me, is how something that at present day looks so static and so robust can be changed, like mountains can be really changed by something so fluid like water. And then I think I'd say specifically, looking at the exact area that I'm looking at, in Patagonia, and sort of what drove me there, I'd say it's a few things. So when we're doing science, especially landscape science, our biggest enemy for really understanding systems and landscapes is ourselves, right? We love changing our landscapes. We love diverting rivers to make, for irrigation. We love building dams for energy. And those are great. They're fantastic things, and allows us sort of develop our land and bring resources to people. But it means that really studying and understanding our landscapes gets harder and harder and harder the more we sort of expand out into the world. So finding rivers and landscapes that are still, quote unquote, pristine is really hard. So we're really pushed almost to like the edges of society, really, to the remotest of remote places where really development hasn't reached yet. So Patagonia happens to be one of these sort of, I don't really like that word, but sort of a final frontier, where you still have these very pristine landscapes, rivers that haven't quite yet been touched by civilization in the sense of building infrastructure around it, or massive re-diversions of rivers. So that is one of the reasons why we went to Patagonia, because it is one of these places that, we can still find these pristine rivers. And I guess that for me, on a very personal level, I'm Brazilian, I'm from South America. And I think, especially as a continent, it's extremely underrepresented in science, and it's extremely understudied, partly because of its, I guess, a general wealth redistribution. A lot of wealth for research comes from North America and Europe. And so it tends to concentrate a lot of research in those areas. Every man and his dog who's a scientist knows something about tiny little glacial valleys in the Alps. But to think that the erosion rate in the rivers draining the largest glaciers in South America and a UNESCO World Heritage Site is still unknown. We're going to be the first ones to actually measure it. To me, is completely crazy, So I guess to me, it's a drive to kind of bring new knowledge and new insight to home in a way.
Maybe it has something to do also with the fact that this research is not exactly easy or cheap to conduct, right? You need some investment to get, you said rock samples, but when I remember your pictures from your last trip, these are like kilos and kilos and kilos of stone that you have to carry along and carry back and then split in the lab. And it's quite a cumbersome process to get to these neat numbers that you have in the end. So you need lots of expertise, and that obviously also costs money, right? So maybe some research institutions are more equipped with that and others less. And then we have another aspect of inequality in Latin America. Funding is not as broad or as amply received as in other institutions. Maybe call for funders to put some money into these institutions. Victoria, before we come to a close here, and we've learned so much about stones and climate and very interesting procedures, can you say something about what you would like to find or to look at? Maybe not after this project is closed, because we know that it's still going on for some time, but what are you looking forward to, or what are you trying to do with this information now for the future?
So I think part of this information, so I think partly because it's so brand new and it's the first, I think what we go and do with it is definitely a case of we'll know once we have it. So I think specifically for this project, because we really are pushing the, kind of the frontier of science at this point. We really don't know what's coming of it. So I guess exactly what next ideas, what drives it, is going to be very based on kind of the results that we get. But what we do want to do with this is we want to, once we have this kind of information, we want to understand better, first of all, how our erosion rates tie to the climate record. So that is the next step. We have a lot of new research coming out of our research group as well that is building a lot of these models and these sort of landscape models and predictive for landscape behavior under these sort of forcings of climate change. So part of what we want to do with this information is start really taking these numbers and these measurements and feeding them into models that can be used in a way to kind of make predictions. It's the whole point of a model is to make a prediction about something. So we want to really use this information to test these models and test our understanding of exactly how river erosion changes under climate change. So that is sort of, I guess, the grand vision.
Any last recommendations that we could already give to people that want to relocate to a riverside or to the seaside, or that want to just be able to breathe in the future when there's no oxygen left because we destroyed the shells of all the ocean animals, or some more positive words maybe?
I definitely would say don't build a house in a river valley, first of all. But also, I would definitely say really push for conservation. I think planting trees, conserving landscapes that we have right now is key to kind of us being able to live in the future, especially as landscapes and climate becomes a lot more variable. Landscapes also become a lot more unstable. And the best thing that we can do to preserve our landscapes is keeping the vegetation where, its original vegetation where it is. So, investing in initiatives that reforest, that revegetate previously degraded land, those kind of things, that is definitely, I say, from a landscape perspective, the way forward.
So you want to invest in planting a tree?
Yeah.
Victoria, thank you so much for this great conversation about your geomorphologist work and your efforts to estimate climate changes of the past and through river erosion, and how we can use that information for our current situation and hopefully conserve our life, because the planet will survive, but maybe also with us if we take better care of it. We're happy that you could be here with us today. And we're also very grateful for you watching another episode of Future Frame TV. I'm Elise Krozer, your host for the Inequalities channel, and we would love to welcome you again for another episode next time when we talk about inequalities. If you want to learn more about it, join in. You can subscribe to our channel on YouTube and or comment, like, share all of the former videos that we already have there. Thank you for watching and hope to see you soon again. Bye-bye.